Good morning, everyone. Myself P. Harita, and I'm here to present today my Tech Talk topic on aerospace propulsion. And my topic is fundamental aspects of solid propellant rockets. Coming to the fundamental aspects of solid propellant rockets, in general, a vehicle is propelled by forces. It is termed as thrust, which provide a desired component of acceleration. These forces can be produced in a variety of ways. Solid propellant rockets are examples of a pure reaction system in which the propulsive forces are produced by the ejection of mass propellants initially contained in the system. Self-contained systems of this type are called rocket motors and can operate in a space as well as in atmosphere. Since they do not require an external propulsive fluid. Solid propellants which come under part in the chemical propellant rockets. Here chemical propellant rockets are divided into two types. We can see that the solid propellants and the liquid propellants, and here we are discussing about the solid propellant rockets. Four categories of rocket motors may be defined according to the physical state of the propellant materials carried within the rocket. There are solid motors, liquid motors, gaseous propellant motors, and hybrid motors. The solid and liquid motors are the hybrid motors. Employing solid liquid combinations are of greatest practical interest because of a heavy tank needed to store large mass of gas. A solid propellant rocket is the simplest form of chemical propulsion. The fuel and the oxidizer both are incorporated in a single solid, means both fuel and oxidizer are mixed and kept in a single solid material called the propellant grain, located inside a container called the combustion chamber. This chamber is large in comparison with the combustion chamber of a liquid propellant rocket. Comparing to the liquid propellant rocket, the combustion chambers, the solid propellant combustion chamber is very huge and large. A schematic illustration of this type of motor can be seen in the next slide. Now here you can see the schematic diagram of solid propellant rocket motor, where we can see the entrance such as the grain, which the where fuel and both oxidizer are stored. We call it as a grain, and we can see the igniter, and we can see the casing which is covering the grain, and at the end we can see the nozzle which will release the exhaust gases to the air. The grain shows here is a tubular with a star-shaped cross-section. Here you can see the second diagram, round-shaped, grain-shaped. It is like a star shape, and a device is called an igniter, which is designed to ignite the burning. Is placed inside the central cavity of the combustion chamber, where the igniter is placed in the central cavity of the combustion chamber. After ignition, hot gases which are produced when we ignite by using the ignition in combustion chamber. The burning takes place, and we can see that it produces the hot gases, and it burns the solid, and it flows through the central cavity and are accelerated to a high velocity by means of nozzle. When we start ignition by using the igniter, it produces the hot gases, and these hot gases produces a solid burns, and these are accelerated with a high velocity, and this will exhaust through the nozzle. During combustion, gases evolve from the solid propellant grain only at its surface. Thus, the surface of the solid regress normal to itself during burning, all the linear regression rate of the propellant grain. The combustion gases come into contact with the outer shell or case of the chamber only at the end of a firing. Means only the combustion comes into contact with the casement. First, it burns in the grain itself where the propellant and oxidizer is mixed. Then, at last end, it comes into the contact with the outer shell. The purpose of the case is to contain the propellant and to withstand the high chamber pressure that are produced during combustion. Where case is used to produce as a, it is used as a protective layer during combustion, where we can see in the figure 1.1a, which emphasizes the simplicity that arises from storing the propellant inside the chamber. The principal parts of a solid propellant rocket are three: Three parts are three, which is considered as the grain, the case, the nozzle, and the igniter. The grain. The grain geometry provides a basics for a preliminary classification of a solid rocket propulsion system. The grain configuration wise essentially depend upon the machine, that upon the thrust and burning time, or more precisely upon the thrust time history. Once the grain is ignited, burning generally progresses until the propellant is completely consumed. The burning surface geometry and its time of evaluation will then impose the thrust time history. The grain is called neutral. If the thrust remains constant during the entire burning history, this occurs this occurs when the total burning surface area does not vary with the time. The graininess will be neutral when when the thrust remains constant. It will be the neutral. When the thrust increases automatically, the surface area of the total burning surface area will vary with the time. When it is burning, the fuel and the oxidizer both are consuming, so the capacity of the grain will slowly decreases with respect to the time. Means it will changes with the time. Case grain. Next case. Case grain also depends upon the application. Two principal types of casing materials are currently employed: metallic materials and glassy materials. Engineering problems arise in connection with the selection of case materials, case manufacturing process, and the trade off between conflicting requirements of lightweight and reliability. It is mainly choosing between the major problems in engineering, where we need to choose the conflict requirements or compulsory requirements are lightweight and reliability, where we can consider the three important elements must be considered in the motor case design. The three important aspects are: the first one is the mechanical load. During motor operation, the case is subjected to a high pressure, several tens of atmospheres. So it should sustain the mechanical load of the motor. The thermal load. Some parts of the case which are in contact with the burned gases must be thermally protected. Means when we ignite, it burns in the combustion chamber. As it comes to the contact with the casing, it should it should be able to resist the capacity of the hot temperature gases. So it should be thermally also. It should be very effective. Next, third, the auxiliary means of thrust vector control. Devices for controlling the direction of the force vector acting on the rocket are structurally supported by the case. These are the three cases we need to keep in mind when we are designing the motor case design of a rocket. Next, the nozzle. The nozzle attached to the downstream end of the rocket motor consists of a convergent section, a narrow diameter throat, and a divergence section. Means CD nozzle. That these three elements are needed in order to accelerate the hot combustion gases, means to move with high velocities required for a efficient production of thrust. Since solid propellant rocket nozzles are generally uncooled, means it is not cold, it is necessary to use nozzle materials capable of withstanding a high thermal load. It should withstand with the high thermal because very hot temperature gases are released during the no, after the combustion. Very it releases through exhaust, which is nothing but nozzle. The manner of thermal protection of the convergence section will depend upon the after end geometry, single or multiple nozzles. Thermal protection of the throat is the greatest nozzle problem because the maximum heat transfer occurs there. The throat must generally be constructed from layers of different materials. The layer that sees the hot gas is composed of a high temperatures refractory or metal material that exhibits a good resistance to erosion. Here we consider the tungsten or graphite covered with tungsten, which is thermally protective to the solid propellant. Coming to the last one, the igniter. The solid propellant rocket motor igniters often consist of an electrically initiated conventional pyrotechnic composition. The combustion of an auxiliary propellant contained in the igniter generates hot gases which comes into contact with the grain surface and induce ignition of the grain. By using the igniter, we can ignite the grain. These pyrotechnic compositions generally consist of a oxidizer metal mixtures. Example, potassium perchlorate aluminum. The igniter combustion often produces hot condensed particles, example solid or liquid aluminum, which impinge on the grain surface, causing high local heat transport and local ignition of a part of the surface area, followed by propagation of the flame to the rest of the grain. For a long rocket motor, sometimes small auxiliary rocket engines are used as igniters in order to provide more nearly simultaneous ignition of the entire grain surface than could be achieved with conventional techniques that rely on the flame spread. This is all about the igniter. These are the major components of the solid propellant. We have seen the case, the igniter, the nozzle, and the propellant grain. This is all about the solid fundamentals of the solid propellant, and thank you.